All right, so the next topic is integration. Integration is part of paper one as well, and there are some concepts that we need to know about integration from P1. For instance, how to integrate expressions like this, mx plus c whole raised to power n. We could use the power rule of integration for this. We add 1 to the power, divide by the new power, and also divide by the derivative of the base, right? There was a condition here that the expression inside it had to be linear, right? This rule only used to work when the expression inside was linear, right? This was one integration rule that you studied in paper one, and then you need to be able to find equation of a curve from its derivative. You integrate that and put a plus c. Whenever you integrate, you have a plus c, right? And to find the value of c, you can use a point that is given for that function. That's what you did in paper one. And then there were area and volume formulas. You also need to use them in paper three sometimes. Area between a graph and x-axis, area between a graph and y-axis, volume of revolution about x-axis, volume of revolution about y-axis. You guys can see my screen, right? Anyone not able to see my screen? Okay, all right. So you need to know the area and volume formulas. Area and volume formulas from paper one: area between graph and x-axis, y-axis, volume of revolution about x-axis, volume of revolution about y-axis. These are not given in the formula sheet. You need to remember them. In the x-axis formulas, you've got y and y square. In the y-axis formulas, you have x here and x square here. Limits are values of y in the second case. And for volume, do not forget the pi outside. Okay, these are the formulas that we've got. You need to use them here as well. Now, what's new in P3 integration? You need to be able to integrate a number of different types of functions. Now, this is one rule that you did in paper one, x raised to power n. That integrates to x raised to power n plus 1 divided by n plus 1. Now, in integration, in the formula, in the general rule that you have, this x can be replaced with any other linear expression, and only linear expression. It can't be a non-linear expression. Okay, so if you were to generalize this, you could say you could have something like this. If you have mx plus c or ax plus b, any of them, it doesn't matter. Mx plus c whole raised to power n. Integration of that would be mx plus c power n plus 1 divided by n plus 1 and divided by the derivative of the part that is inside. The expression that x is replaced with, whatever expression x is replaced with, that expression has to be a linear expression. Only then this rule would work. And then we have a number of other rules that are given in the formula sheet. First of all, we've got e raised to power x. E raised to power x, that integrates to e power x. Integration of sine x is minus cos x. Integration of cos is sine. Integration of secant square is tan. These are functions that can be integrated directly. Okay. If x is replaced with any other linear expression in these, then the rule remains the same as before. There's one additional step, and that is that you also have to divide by the derivative of that expression. That will be m, so you divide by that. And again, expression. For using these rules, you can only have a linear expression in place of x. If it's something else, then you cannot apply these rules. Okay. Now, these are some rules that are given in the formula sheet directly. You need to be able to use them. For instance, if you had minus 3 over 4, minus 3 over 5 into sine of 4x plus 1, minus 3 over 5 is a constant that remains as it is. Integration of sine is minus cos, so it becomes minus cos of 4x plus 1 divided by 4. Similarly, if you had e raised to power minus 2x plus 5, integration of e power something remains the same, but you have to divide by the derivative of this expression, that's minus 2, and that becomes your integration. So these are some functions that can be integrated directly. Then there are some more functions that can be integrated directly, and they come from the differentiation page on the formula sheet. We learned in differentiation that the derivative of secant x is secant x tan x. derivative of cosecant x is minus cosecant x cot x, and derivative of cot x is minus cosecant square x. Now, these rules are not given in the formula sheet for integration. On the page for integration, you don't see these rules. However, you sometimes need to use them as well. So you'll make them yourself. Just reverse the rules that you had on the differentiation page of the formula sheet. So let me show that to you. We looked at them when we did differentiation just now. Differentiation of secant x for secant x tan x, this was minus cosecant x cot x, this was minus cosecant square x. Now, integration is just the opposite of differentiation. So for integration, we can have the opposite rules. These would be the rules for integration. So that's where these come from. You need to be able to use them as well. Integration of secant x is secant x tan x is secant x. Integration of cosecant x into cot x is minus cosecant x. And integration of cosecant square x is minus cot x. And again, x could be replaced with any other linear expression as well. So in general, you could say if you have secant of mx plus c into tan of mx plus c, that integrates to secant of mx plus c divided by m. If you have cosecant square of mx plus c, for instance, that integrates to minus cot of mx plus c divided by m, and so on. So these are expressions, these are functions that you should be able to integrate directly. You should be able to integrate these directly. Okay. Integration of secant x, that's not part of our syllabus. Integration of secant x is not part of our syllabus. That will become 1 over cos x. We don't need to be able to integrate that. Okay. So these are functions that can be integrated directly. All right. And x can be replaced with any other linear expression in these. In that case, we would divide by m as well. M would be the derivative of that linear expression. These are used very rarely, but you need to know them. I have seen them tested at least once in recent papers, maybe twice. I'm forgetting about the second instance, but definitely once. So in very recent papers. So you need to use these rules. You need to remember these rules or be able to make these rules using the differentiation formula sheet. So if you have minus 3 over 5 into secant square of minus 4x plus 1, integration of secant square, what's that? That is tan. Integration of secant square is tan, so that minus 3 over 5 remains as it is. Tan of minus 4x plus 1 divided by minus 4, that's the result that you get from this. Minus 5 into cosecant of 2x into cot of 2x. What about this? This is given in the formula sheet directly. If you do not remember them, if you do not remember that there's a rule that exists for this directly, then you would think of integrating this by parts and you would get stuck. You would not be able to do it. Okay. This can be integrated directly. Even though it's a product, we know the integration for this directly from here. Cosecant x cot x, that integrates to this. Unless you remember this, you'll not be able to do this in the exam then. So you have to remember that a rule exists for this. At least that much you need to remember. Then you can have a look at the formula sheet and see what exactly that rule is. So cosecant into cot, that integrates to minus cosecant. Okay. So you'll say minus cosecant of 2x divided by 2, minus 5 outside remains as it is. You simplify this and that gives you the integration. Now this is from an actual paper. 5 tan of 2x over cos of 2x. How would we integrate this? Now looking at this, it looks fairly complicated, right? It's a fraction. You think of all the fraction rules that you could apply on this. You think of bringing this to the numerator and then applying integration by parts, but it turns out tan of 2x over cos of x, if you bring cos 2x to the numerator, it actually becomes secant, right? Cos, when you bring that to the numerator, that will become secant, and you end up getting secant into tan. And for that, we know that a direct integral exists. We can integrate it to secant directly. So we bring cos to the numerator. When we bring cos to the numerator, that becomes secant, and we get this expression, integration of secant 2x into tan of 2x, that's secant 2x divided by 2. The 5 remains outside as it is, and you get that integration directly. Okay, so you don't have to use integration by parts or any other rule in this case. It's given in the formula sheet directly. You just have to, change this slightly, change cos to secant, and then integrate that. If we have this, if we have a non-linear expression in any of those functions, you cannot integrate it like this. For example, if you had this 3x squared plus 1 whole squared and you wanted to integrate this, you cannot use the power rule on this. Why? Because this expression is non-linear. In this case, you could still integrate it by expanding this first. So this is a square. You could use a plus b whole squared to expand this and then integrate one term at a time. But if you had, for instance, something like this, if you wanted to integrate, for instance, sine of x squared plus 2, we can't do that. This is not the same. This is not going to be minus cos of x squared plus 2 over 2x. That would be wrong. Why? Because this rule does not apply because this thing is non-linear. This expression has to be linear for this to work. Okay. All right. We cannot do this by substitution as well. We would need something else outside. If we had an x multiplying outside, then they would give you a substitution themselves that you could use to integrate it. But if it's just this, then this cannot be integrated using the rules that we know until now, know in A levels. Okay, so these are some standard rules that we saw earlier. Now we've got some rules that we will be using to integrating for integrating fractions. Okay, so we have a number of rules for integrating fractions. The first of them is what we will be calling the ln rule. Now, what's the ln rule? This is a simple example of that. 1 over x that integrates to ln x. That comes up a lot, so you need to just remember this. It's given in the formula sheet as well. 1 over x that integrates to ln x. But in general, whenever you have an expression like this, in the formula sheet, it says something like this: f dash of x divided by f of x that integrates to ln of f of x. In simple terms, what that means is, if you have a numerator, that is the derivative of the denominator. If numerator is the derivative of the denominator, integration of that fraction is log of the denominator. It's ln of the denominator. That's the integration. If numerator is the derivative of the denominator, that integrates to log of denominator. That's the rule. We call this the ln rule. Whenever you have a format like this, where numerator is derivative of denominator, we integrate it using this rule. For example, if you had minus 4 over minus 4x plus 1, now what's the derivative of denominator? That's minus 4. We have minus 4 in the numerator. So we can say the integration of that is just ln of minus 4x plus 1 plus some constant. If you have this fraction, look at this. What's the derivative of the denominator? 10x plus 3. We have that in the numerator. So that integrates directly to ln of 5x squared plus 3x minus 2. And both of these examples, we already had that exact form that we wanted. Numerator was the derivative of denominator. So we can integrate them. We could integrate them directly. But sometimes you end up getting something like this, in which it is not exactly that form already, but you have to change something in that to make it that form. For example, if you have 10 over 5x minus 3, what's the derivative of the denominator? The derivative of denominator is 5. We want 5 in the numerator, but we have 10 instead. What we can do is, we could say, let's take 2 common out of 10. So that gives you 2 into 5. Now, 2 is just a constant. We could write that outside the integral as well, because a constant that's multiplying, that does not change due to integration. So this constant can just be written outside the integral as well. So we write 2 outside, and then inside we just have 5 over 5x minus 3. That is exactly the form that we wanted. Numerator is the derivative of denominator. The integral becomes ln of 5x minus 3. Another way of thinking about this could be that's a more general way that will work in most of such examples when integration using ln is possible. If you have 10 over 5x minus 3, you could say, whatever is the number in the numerator, just write that outside. Just write that number outside. So you write 10 outside. If you write 10 outside, what are we left with inside? 1. Now, we want 5, so we multiply by 5, and to balance that, we divide by 5. Now, actually, we would be multiplying and dividing by 5 inside, right? So logically, we multiply here, and to balance that, we divide here as well. But since it's just a constant, it's our choice to write that inside or outside, and we choose to write that outside so that the inner part, that just becomes that that ends up becoming that format that we want, in which numerator is the derivative of the denominator. So we have 5 over 5x plus minus 3 inside. Numerator is the derivative of the denominator, and that gives us the result. Now, that method becomes much more helpful when you have something like this, in which it's not easy to figure out what we would have to take common to make it that number. For example, if we had 7 over 5x minus 3, what we want in the numerator is 5. How can we have 5 in the numerator? You could say, let's write 7 outside. Inside, you would just be left with 1 in that case, right? When you write 7, when you take 7 common outside, now we want 5 instead of 1. So what we do is we say, let's put 5 here, and to balance that, let's divide by 5 outside. And now we've got 7 over 5 outside. This is the log form. It can be integrated to ln of 5x minus 3, and that's the result. Let's take this example. You have minus 4x squared plus 6x minus 7. What's the derivative of the denominator? The derivative of the denominator is minus 8x plus 6. So we want minus 8x plus 6 in the numerator. Can we have that somehow by multiplying or dividing by some constant? We have minus 4x plus 3 right now. Can we make it minus 8x plus 6 somehow? We could multiply by 2. We could multiply by 2, and that will make it minus 8x plus 6. But to balance that, then we divide by 2 outside. And now inside the integral, we have that form where numerator is the derivative of denominator. So the integration becomes ln of the denominator, and that's our result. Now, if we had 2 over x squared plus 9, what's the derivative of the denominator? The derivative of the denominator is 2x. So we want 2x in the numerator. We already have a 2 there. So we could think of multiplying by x and then dividing by x outside, but that does not work. We can only multiply and divide by constants, not by x. Because if you were multiplying and dividing by x, that multiplication division is actually happening inside. So x over x like this, for instance. Now we can't bring this x outside. That only is possible for constants. We can only write constants that are multiplying outside the integral. We can't pick up x from there and write that outside. That would not make sense, right? So this multiplication and division that we're doing, that is only possible with constants, not with x. You're not allowed to write x outside. Okay, multiply or divide by x. You can only multiply and divide by constants to convert it to that form. So this thing cannot be integrated using the ln rule. And as we will see later, this would actually be integrated using the tan inverse rule. Okay, we will see that. Now, you need to remember that two specific functions, tan x and cot x, they are integrated using the ln rule. You need to memorize this. Otherwise, you would not be able to figure this out in the exam yourself. You need to memorize that tan and cot, they are integrated. They are integrated using the ln rule. Tan can be written as sine over cos, right? So if you have tan of x, you can write that as sine over cos. And now, what's the derivative of cos? Derivative of cos is sine, is minus sine. Right now, we've got sine over cos. We want minus sine in the numerator. So we can put a minus here, and to balance that, put a minus outside. And now the inner part that follows that rule, numerator is the derivative of denominator. So the integration becomes log of the denominator, and we have a minus sign outside. And that's the integration. You can leave it like this, and that's perfectly okay. Another way to write this could be that you could take this minus 1 to the power. So it becomes cos of x power minus 1, which is 1 over cos x. And then you could write that as secant x as well. So this is also another way of writing the integration of tan. Integration of tan is done using the ln rule like this. Similarly for cot as well. Cot is also integrated using the ln rule. What we do is we write cot as cos over sine. Now it could be some other expression in place of x here as well. It does not necessarily have to be x. It could be something else as well. For example, in this case, we've got 3x. We could write cot of 3x as cos 3x over sine 3x, right? Now, when we do that, what's the derivative of sine 3x? Derivative of sine 3x is actually 3 cos 3x. We only had cos 3x in the numerator. To make that 3 cos 3x, what we do is we multiply by 3 inside, and to balance that, we divide by 3 outside. And now the inner part, this follows that condition where numerator is the derivative of denominator. So integration of this is going to be just log of sine of 3x, and we have this 1 over 3 outside as it is. That's what the integration becomes. This is something that you need to remember. Tan and cot, they are integrated using the ln rule. Okay, you need to memorize this. Okay, this is just an example here. You can have a look at this in your own time. 2 over x minus 2, for instance, both of these methods for integrating it are correct. One way is that you write 2 outside, and then that form becomes the ln form inside, and that becomes 2 ln of x minus 2. Another possibility could be that you could multiply the denominator by 2, which is kind of a weird way of doing this. But if you end up doing something like this, then you have 2 outside as it is, and this is now the log form, and that might turn out to be this. Both of these are acceptable, right? So sometimes you end up getting a slightly different form than the marking scheme, but that might be equivalent in some cases. In this case, the C's would be different for both of them, but both of these are acceptable integrals. Okay, even though they are not identical to each other, they are still equivalent because the difference is only of a constant. So the C's will be different and it will be the same expression. Okay, some people just get confused. Sometimes they end up getting a different answer slightly from the marking scheme. And a lot of times it is the case that it is equivalent to what they have in the marking scheme. So this is also acceptable. Okay, let's move on. Let's have a look at the next rule now. That's tan inverse rule. Now, what is tan inverse rule? This is how it's given in the formula sheet. 1 over x squared plus a squared. If you have an expression of this form, that is integrated to 1 over a into tan inverse of x over a. Right? That's the rule that we've got. For instance, if you have something like this, 1 over x squared plus 4, the rule is 1 over x squared plus a squared. That has to integrate to 1 over a into tan inverse of x over a. So we could write this like this: 1 over x squared plus 4. We could say it's x squared plus 2 squared. And then the value for a is 2. We just apply that rule. It becomes 1 over 2 into tan inverse of x over 2. Okay. And that gives you the results. That gives you the result. Okay. Similarly, you could have something like this: minus 5 over x squared plus 36. How do we use that rule here? The rule is, if you have 1 over x squared plus a squared, that integrates to 1 over a into tan inverse of x over a. Now, in this case, we've got minus 5 in the numerator. If you want, you can write minus 5 outside, and that just leaves you with 1 inside. So that becomes that form. In the denominator, you have x squared plus 36. You could say that x squared plus 6 squared, and then that integrates using the tan inverse rule. Minus 5 remains as it is, 1 over a into tan inverse of x over a. Simplify that, and that gives you the final integral. The value for a in this case is 6. Now, how would you know that something can be integrated using tan inverse? How do you figure that out? The standard form that you would have for that, remember, for ln, numerator should be the derivative of denominator, or you should be able to make it that by multiplying or dividing by some constant. For tan inverse, how do you figure out that something can be integrated using tan inverse? This is the form that you would need for that. The numerator should have some constant. It should be a constant, only a constant. And the denominator should have an x squared term plus some constant term. Okay. Numerator should just be a constant. Denominator should be x squared term plus some constant. That's what the denominator should be. Okay. If it is this form, then we can use the tan inverse form. However, for using the tan inverse form, for applying this formula, we would first need to make the coefficient of x squared 1. If it is not already 1, we would have to make it 1 first of all, and then apply that formula. Okay, so this coefficient will have to be made 1 first of all. It could be something else originally, before we apply this rule, we should make that 1 and then apply this rule. Only then this rule would work like this. Now, let's have a look at some examples of that. If you had 4 over x squared plus 3, for instance. Now, in this case, we have a problem that this number is not a perfect square. Okay, 3 is not a perfect square, so it does not necessarily have to be a perfect square. We could write, first of all, 4 outside. If we write 4 outside, inside we're left with 1 over x squared plus 3. Now, how do we write this in square form? Because we want a squared there. Now, it's not perfect square. We could write it like this. We could say that's the same thing as saying under root 3 whole squared, right? So the value of a that you have here is under root 3. Now we can apply that rule. It becomes 1 over under root 3 into tan inverse of x over under root 3. You have 4 outside multiplying, and you can simplify that to get the result. If we have something like this, minus 5 over 3x squared plus 48, what about this now? We could take minus 5 common outside, write it outside so that we have 1 left inside. However, in the denominator, now we have a coefficient of x squared, that is 3. Now, we want this coefficient to be 1 to be able to use this rule. So what we do is we take 3 common from the denominator as well. When we do that, inside we're just left with x squared plus 16. And then we could write that as x squared plus 4 squared. And then on this part, we could apply that tan inverse rule, 1 over a into tan inverse of x over a, 1 over 4 into tan inverse of x over 4. Okay, and then you simplify that, you get the integral. This is as complicated as it could get sometimes, that you have something like this. If you take 7 common outside, that leaves you with 1 inside. In the denominator, you have 2x squared plus 5. You take 2 common outside, that leaves you with x squared plus 5 over 2 inside. Now, it's a fraction that you have. How do we deal with this now? We could write 5 over 2 as square root of 5 over 2 whole squared, and then apply that rule now. 1 over a, that's the value for a that we've got now. The integration becomes 1 over that into tan inverse of x over that. Right, and then you simplify this. You can just put this on your calculator, put this thing on your calculator, and that will simplify to this, okay? And then inside tan inverse, this 2 will go to the numerator, and it becomes under root 2 over 5 times x, which is outside the square root, and that's your integration. Right, this is as complicated as it could get sometimes in case of tan inverse rule. So that's the second rule that we've got, ln rule, tan inverse rule. The next is integration using partial fractions. What can also happen is none of those rules might work, the ones that we discussed earlier. And instead, you could have some factors in the denominator. So for instance, let's say you have minus 20 divided by x plus 2 into 2x minus 6, right? That's the fraction that you've got. Minus 20 over x plus 2 into 2x minus 6. Now, how would you integrate this thing? How do you integrate this thing? In the denominator, you have 2 factors. You will find partial fractions of this. You'll break it into 2 parts. Using the partial fractions method, you just apply that whole method, break it like this, and then you integrate those 2 fractions separately. So you integrate these 2 separately. Now, in this case, they can both be integrated using the ln rule. In the first fraction, you could write 2 outside, so you have 1 over x plus 2 left. That's the standard ln form. In the second case, you want 2 in the numerator. One way to do that could be that you take -4, that you write -4 outside, and then you multiply by 2 inside, and to balance that, you divide by 2 outside. And now the inner part becomes the ln form. You can integrate that directly and you get the result from that. Okay. All right, so sometimes you could have an expression like this, 15 over 2x squared minus 14x plus 24. Now, this is not factorized. This form is not factorized. Now, since this form is not factorized, you can first think of whether the ln rule works. Does that work? The ln rule requires the numerator to be 4x minus 14. Now, we can't have an x in the numerator. We can't bring x ourselves. So ln rule will not work. It's not tan inverse form. In tan inverse form, we just want an x squared term plus some constant. Now, in this case, we have an x term as well. So that would not work. It's not tan inverse form. can we factorize this? Sometimes you have to factorize the denominator yourself, first of all. So in this case, the denominator can be factorized. It can be factorized to x minus 3 into x minus 4. And you have 2 taking common outside here in this case. And then once you have this form, then you find partial fractions for that and then integrate both of them yourself, right? So sometimes you may have to factorize the denominator yourself as well. That is also possible. And then find partial fractions and integrate those fractions separately. Let's take this example. If you have 24 over x squared minus 9, this is, again, not a factorized form, but you could factorize this yourself. So it becomes x plus 3 into x minus 3. You could find partial fractions for that, integrate those two separately, and you get the result from that. In the previous example, it's not necessary that you take 2 common outside. It could be done without that as well. In this case, it just simplifies things. You could take that common outside, but if you don't, then you could have that in one of these factors, and that's perfectly okay. That would also work. Okay, now, if you had something like this, 24 over x squared minus 9, for instance, we saw that we could factorize the denominator using a squared minus b squared. That will be a plus b into a minus b. A squared b a plus b into a minus b. It could be factorized like this. And then we could use partial fractions in this. Tan inverse form cannot be used here because tan inverse form requires x squared plus some constant. This is minus. We want x squared plus some constant. Having a perfect square is not a condition. Even if this was not a perfect square, we could write that in square root form and then whole squared. The problem is this minus sign. Tan inverse requires a plus sign. You can't have a minus for that. When you have minus, you can factorize this and then break it in partial fractions and then integrate those two separately. However, this whole working is not required because the form that you have here, it is actually a standard form that is given in the formula sheet directly as well. If you look at the formula sheet, you would find that you have the tan inverse rule written here, 1 over x squared plus a squared. That is 1 over a into tan inverse of x over a. And along with that, you've got 2 other forms written. That's 1 over x squared minus a squared and 1 over a squared minus x squared. You have these integrals written directly in the formula sheet. If you have x squared minus a squared in the denominator with a constant in the numerator, that integrates to this. And similarly, a squared minus x squared, that integrates to this. So the form that we had here that I showed you earlier, although the logical way of doing this is using partial fractions, however, if you give you this question, that will only be like 2 marks. So this will be a lot of working for that. It will be 2 marks because they have given this rule directly in the formula sheet. You should be able to use that directly. It's the form that's similar to tan inverse. The only difference is there's a minus in the denominator instead of plus. In that case, you can use these rules directly. So we can say that these are 2 specific cases, special cases of partial fractions that we directly know the formulas for. So if you have 24 over x squared minus 9, you could say that can be written like this: 24 outside over into integration of 1 over x squared minus 3 squared. A is 3. A is 3, so it becomes 1 over 2 times 3 into ln of x minus 3 divided by x plus 3. That's what the integration becomes. That's what we got after so much working earlier using partial fractions. Since it's given in the formula sheet directly, we just use that like this and get the result. Similarly, if you had 25 minus x squared in the denominator like this, for instance. Now this is this last form that's given, constant minus x squared. We could use this rule like this here as well. We could write minus 4 outside, and then inside we have 1 over 5 squared minus x squared, and it becomes exactly this form, which can be integrated using this rule directly, and we get this result from that. Okay, so what are the rules that we've discussed for partial fractions and discussed for fractions until now? ln rule, tan inverse, partial fractions. For partial fractions, sometimes you'll have the factorized form given already, or you would have to make it that yourself. The question will not always tell you to use partial fractions. Sometimes they would. sometimes they won't. So you would have to do that thinking yourself if you can factorize that or not. Another possibility is, it's not a rule as such, but just a trick that you need to keep in mind that will help you integrate some fractions when one of those rules does not directly work. If you have 5x minus 9 over x squared plus 16, now ln rule does not work here because that requires 2x as the numerator. We've got this constant as well. We can't make it just 2x. We'll have a constant as well. So we can't, this is not ln form. This is not tan inverse because tan inverse requires only a constant in the numerator. We have an x term as well. So if we just had this, we could use the ln rule. If we just had this, we could use the tan inverse rule. So what we do in some cases like this is that we split the fraction, we split the numerator. So we write this fraction as 5x over x squared plus 16. We write that separately, and we write minus 9 over x squared plus 16 separately. We break it into two fractions because if you have something like this, a plus b over c, that can be written as a over c plus b over c. They are equivalent to each other. That's not the same as splitting the denominators. That's not possible. That would be incorrect. You can't split the denominator like that, but the numerators can be split like that. So we can just split the numerator this way. And then the first fraction that can be integrated using the ln rule. We want 2x in the numerator. We will write 5 outside, multiply by 2 inside to balance that, divide by 2 outside. And here we could use the tan inverse rule, and that would give us the result. This is something that we can call integration by splitting the numerator. Splitting works when you have to think of it that after splitting, would you get something that you can integrate then? So you have to think of that first. So when you split this in this case, you can think of this in your head that yes, this is something that you can integrate using ln, and this is something that you can integrate using tan inverse, right? So you'll have to think of whether that's going to be of any benefit or not. So in this case, that is of benefit, and we could do it like this. All right. In this case, in these cases as well, if a is not a perfect square, for example, if it's 3, you could write that as square root of 3 whole square, just like we could do that for tan inverse form. We could do that in this form as well. We could write that in square root form, and that will work. Okay. Similarly, if we could have an example like this: 7x minus 5 divided by 2x. If you want to integrate this, again, we could split it into two parts. We could say, let's write 7x over 2x separately, 5 over 2x separately. Now the first one, that just becomes a constant, which can be integrated to 7 over 2 times x. The second one can be integrated using the ln rule. Then if we write 5 into outside, we have 1 over x left, and that's 1 ln of x, and that's your final result. That's how you could integrate. Sometimes you can simplify your integral by splitting the numerator like this as well. The denominator in this case cannot be factorized. That's a very common error that ends up happening. Sometimes this is a squared plus b squared. There's no factorization that you can do for that. A squared minus b squared can be factorized. A squared plus b squared can. You can't factorize this. Okay, then another possible form is when you have improper fractions. Improper fractions. How do you integrate improper fractions? Improper fractions in this case would be when the numerator, the degree of the numerator is greater than or equal to the degree of the denominator, right? When numerator's degree is greater than or equal to the denominator's degrees. For example, in this case, this is an improper fraction. For improper fractions, the process for integrating is this, that we break them into two parts: quotient plus remainder over divisor. We apply the division process. Find the quotient, find the remainder, and then that fraction that we had, we break it into two parts: quotient plus remainder over divisor. And then after breaking it into two parts, we integrate those two parts separately. This could be integrated separately. This could be integrated separately. The first one using simple power rule. The second one using tan inverse, as you can see here, and that gives you the result. Okay, so these are all the different ways that you have for integrating fractions. Ln rule, tan inverse rule, partial fractions, then two specific forms of partial fractions that are written directly in the formula sheet, 1 over x squared plus x squared minus a squared, 1 over a squared minus x squared. And then you could split the numerator or you could have an improper fraction, right? So you need to remember all of these rules. Okay, now next, we see what happens when we have products. When we have two things that are multiplying, that's a product. We can integrate that using something that we call integration by parts. Okay, it's the product rule of integration. When two things are multiplying, one way to integrate them is using integration by parts. If the question does not give you any other idea, for example, substitution, this is what you would be doing in most cases. Now, how does integration by parts work? If you want to integrate something like this, x into sine x, for instance, the formula that's written for that's given for integration by parts in the formula sheet looks like this: u into dv over dx, integration of that is uv minus integration of v into du over dx. We'll write that in a relatively simpler form. We'll say it's u into dv over dx, that's just v dash. So integration of u into v dash, dx just means it's with respect to x, right? So that's understood. We'll ignore that. That is given by u into v minus integration of u dash, right? That's how we will write that formula. That will simplify things for you. Integration of uv dash, that is uv minus integration of u dash, right? That's the formula that we'll be using. Now, for example, if you had x into sine x, you can say x is u, sine x is v dash. Now, in the formula, you want uv minus integration of u dash. So you want the value of u, you want the value of v, you want the value of u dash and v dash. Now you have u equal to x, you've got v dash equal to sine x. From u, you can find u dash by differentiating. The derivative of x is 1, so u dash equals 1. V dash is sine of x, integration of sine x is minus cos x, so v turns out to be minus cos x. Now, once we've got these four values, u dash, v dash, we can just input them in this formula and then simplify that. That gives us the result u into v minus integration of v into u dash. Simplify this and that gives you the result. You can see what that turns out to be. That's how this integration by parts formula works. This is another example. You can have a look at that. U is x here, v dash is e power 3x. All you have to do is find the derivative of u to give you u dash, find the integration of v dash to give you v, input values in this formula and simplify that. That should give you the result. Now, the choice of u and v dash is important here. You can't just randomly take one of them as u and the other v dash, because sometimes otherwise you would not be able to find the integral. For example, in this case, if you take sine x as u and x as v dash, then you end up getting stuck, because when you apply the integration by parts formula once, in the second step, you end up getting a product again. Getting a product again is not an issue, but this product that you're getting is actually more complicated than what you started from. You started from sine x into x. That's what you started from. In the next step, you're getting x squared into cos x. So the power of x is actually increasing. The integral is becoming more complicated. So that means you're not going in the right direction. There's something wrong. So in such cases, it's important to know which one you should be taking as u, which one you should be taking as v dash. In fact, we've done this example before, x into sine x. I wrote that as x sine x earlier. In that case, we took u as x and that worked. Taking u as sine x does not work. So how do we decide what to take as u and what to take as v dash? The logic behind this is that, first of all, v dash should be something that you are able to integrate directly, because v dash has to become v. If you don't know how to integrate something, then taking that as v dash would not work. For example, if you had ln x somewhere, you don't know what the integration of ln x is. If you take that as v dash, then what would v be? You would not be able to find that. So v dash should be something that you can integrate directly. For example, it could be some algebraic expression, x raised to power something. It could be sine cos. It could be exponential, you know how to integrate them. If both the expressions can be integrated, then what we do is we take u as the one that becomes simpler after differentiation. For example, if you have x cubed after differentiation, or let's actually take x squared, for instance, after differentiation, it becomes 2x. It's becoming simpler after differentiation. So u should be something that becomes simpler. Sine, for instance, that does not become simple. Sine becomes cos after differentiation. That's not becoming simple. Ln x does become simple. It becomes 1 over x, right? So u should be something that becomes simpler after differentiation. Now that's the logic, but eventually the result that we get from that is, this is a rule that we would remember to decide what to take as u and what to take as v dash. You can remember this as I late. We use this for integration by parts for deciding between u and v dash. Remember these initials I, L, A, T, E, I late. I stands for inverse trigonometric function. In your syllabus, there's only one, that's tan inverse. L stands for log, and again in your syllabus, it's only ln, for which you have to do the integration or differentiation. A means algebraic. Algebraic means powers of x raised to power something. It includes constant as well, right? So constant could be thought of as x power 0. So we would include constant in algebraic expression as well. T stands for trigonometric, sine, cos. E stands for exponential, e raised to power something. Now, in I late, whatever is on the, so you'll have two expressions, right? Out of those two expressions that you have, whichever is to the left side, you would take that as u. Whichever is on the right side, you will take that as v dash. For example, if you had something like this, that one expression was trigonometric and another was algebraic. Now, algebraic and trigonometric, out of these two, algebraic is on the left side, you take that as u. Trigonometric is on the right, you take that as v dash. If you had algebraic and, for instance, log, what would happen in that case? Amongst these two, algebraic is on the right, we take that as v dash. Log is on the left, we take that as u. So in I late, whatever is on the left side, you take that as u. In I late, whatever is on the right side, take that as v dash. For example, if you have cos of 3x into x, we want to integrate this. We've got two types of functions. One is trigonometric, the other is algebraic. Trigonometric is on the right, we take that as v dash. Algebraic, we take that as u equals x, v dash equals this, and then we just input values in the formula, and that gives us the result. Okay, so that's how we decide between u and v dash, which variable to take as u and which one to take as v dash. Sometimes you may have to do integration by parts multiple times as well. So for instance, if you have x squared into e raised to power 4x and you want to integrate this, how would you do that? If you were to do integration of this, first of all, you have to decide between u and v dash. What do you take as u and what do you take as v dash? X squared is algebraic. X squared is algebraic. And e raised to power 4x is exponential. Amongst these two, a is on the left side, that is u. E is on the right, that is v dash. Okay. So we take u equal to x squared, v dash equals e power 4x. Apply integration by parts, but in this case, what happens is we end up getting a product inside the integral again. When we apply this process, this is what we end up getting, e power 4x divided by 4 into 2x. Now, I would generally recommend that you write down any constants that are multiplying outside. That will simplify things for you. So for example, in this case, you have 2 in the denominator. You can write that outside like this, 1 over 2. And inside, you're just left with this now, e power 4x into x. Now, we again are getting a product. How do we integrate this product? We would have to apply integration by parts again in this case. Now, this can happen sometimes as well, that you have to apply integration by parts multiple times, but make sure that you're going in the right direction by checking that the integration is becoming simpler than before. So you started from x squared into e power 4x. Now you've got x into e power 4x. So the power of x is decreasing. So it is becoming simpler. That means you are going in the right direction. Apply the integration by parts process once more, and then you would be able to get something simpler like this, which can be integrated directly, simplify everything, and you get the result from that. So sometimes you may have to apply integration by parts twice as well. Not more than twice, at least until now, they've not asked you to do this more than twice. But twice is very common. You may have to do this. Okay. This is another example, x cube into ln of 2x, you can integrate it using integration by parts. It's also a product. In this case, one is algebraic, the other is logarithmic. You'll take the logarithmic as u, right? Because that's on the left side there, and algebraic as v dash. Find u dash and v, input them in the formula, and you get the result from that. You can have a look at this working. Now, for ln rule, we remembered that whenever we have tan of something or cot of something, we would always be using the ln rule for that. Here as well, you need to remember two functions that will be integrated using integration by parts. Sometimes they will give you a hint in the question. They will tell you to use integration by parts. Sometimes they won't. You need to remember that they're integrated like this. The first one is ln of x. So integrating ln x, the process works like this. We write it as 1 into ln x. We don't know the integration of ln x directly, right? It's not given in the formula sheet. Ln x, derivative of ln x is 1 over x, but integration of ln x, we don't know. So integration of this function works like this. We write it as a product 1 into ln x. Now it becomes a product. And then we apply integration by parts in this. Remember, we said constants will be treated as algebraic. So we treat this as algebraic. 1 is algebraic. Ln x is logarithmic. So u equals ln x and v dash equals 1 according to IL8. So in IL8, on the left side, you'll have u. On the right side, you would have v dash, right? So log is on the left side, algebraic is on the right amongst these two. So you would take log as u. Apply integration by parts, you get the result. Similarly, the other function is tan inverse. Tan inverse is also integrated using integration by parts. You need to remember that as well. Tan inverse is integrated using integration by parts. Okay, you write this as 1 into that as well. So tan inverse of 4x, we could say that's 1 into tan inverse of 4x. And then we apply integration by parts. U equals tan inverse of 4x, v dash equals 1. Find u dash and v, input them in the formula. When you do that, the integration that you get in the next step, that's going to be a fraction. And this fraction in this case can be integrated using the ln rule, right? We've got x over 1 plus 16x squared. The derivative of the denominator is 32x. So we wanted 32 in the numerator. We could multiply 32 in here and divide by 32 outside to balance that. And then it becomes the ln rule. We integrate it like that, and that gives us the result. So you need to remember ln of something and tan inverse of something, they are integrated using integration by parts. We write them as 1 into that function and then integrate them. Okay. This is another method that's used very rarely, but it's good to know. If we have to integrate, for instance, in sine x into cos x. Now, there are multiple other ways of integrating this as well, but this is one way of doing this, integration of sine x cos x, but this method works for some other kinds of problems which are a bit more complicated. But let's understand it using this example. Sine x into cos x, if you were to use integration by parts in this, since it's a product, you could say u is equal to sine x, v dash equals cos x. Both are trigonometric. It doesn't matter which one you take as u, which one you take as v dash, because both are trigonometric, right? Both are t's in IL8. So it doesn't matter. You can take any of them as u, any of them as v dash. If I take this, then what happens is, in the next step, I get sine x into sine x minus integration of this thing. And this is actually the same thing that we started from. So it's not becoming any simpler. It's a loop that is started, and this will just continue like this forever. If I keep doing this, I'll keep getting integration of sine x into cos x. So that's a loop that's appearing here. What we can do in this case is we could say this integration, let's call this something, let's denote it by some letter. Let's call this I, for instance, or any letter for that matter. It doesn't really matter. you could say this is I. That's what we want to evaluate. So I equals this thing. Now we are getting that same thing here. So this is also I. So we could replace this with I here now. So we have I equal to sine square x minus I. What were we trying to find out? We were trying to evaluate I here. So what we do now is we make I the subject. So it becomes 2I into sine square x, and then I equals half sine square x. And that means integration of sine x into cos x, that is half sine square x. Okay, we can call this the loop method. And that is used when you apply integration by parts and you get a cyclic expression that, you get the same thing back again that you started from. It's not getting any simpler. It's just giving the same thing again. In this case, you can make a loop like this. When you have this same thing again that you had initially, you can replace that with that expression, for instance, just that letter, call it I, for instance, and then just make I the subject, and that gives the result. Okay, there's a Azan going on here. We have a 1 minute break. I'll show you a more complicated example of this. You can have a look at this, try to understand what's going on, and then I'll explain that. Just 1 minute. I'll be back in a minute. Okay, so this is another example of that loop method. So you've got an exponential function, and you've got sine of 4x. You've got these two functions. Now, both of these functions do not get any simpler, right? E raised to power x into sine of 4x, they both don't get any simpler. When you apply integration by parts once, you get this e raised to power x into 4 into cos of 4x, and then this is not getting any simpler, right? It's the same difficulty level, as same complication level as before. One exponential function, one trigonometric function, but it's not the same thing as well. It's something different, right? So it's not becoming a loop yet. However, when you apply integration by parts once more on this, what happens is, in the next step, you do end up getting something like this: e raised to power x into sine of 4x, right? So if you look at this working again a bit slowly later, I've just taken the constant outside. And then inside you're left with e raised to power x into sine of 4x. And that's exactly the same thing that we started from. So we have a loop now. We could say that original thing is I, right? Then this could also be replaced with I. So we've got I here, we've got I here. We could make I the subject now, and that would give us the integration. Okay, so that's a method that you can sometimes use in integrals like this that do not become any simpler, but when you integrate them, you end up getting the same thing from that again. It's very rare. You would just find 1 or 2% at max in this in past papers, and all that those two in some older papers. But it's good to know. There's always a chance that they end up giving something like this. So you should be aware of this. Okay. All right. Then you have this rule that we call the extended power rule. Now, this is not part of your syllabus explicitly, but it simplifies some integrals. Okay, you can do everything without it as well. There are other methods that you've done, they will work, and you would be able to integrate such functions using those methods. However, this rule will simplify some integrations. I'm calling this the extended power rule. It's the power rule, but it's the extension of that rule. So earlier we said the power rule, we would only be applying that on these expressions. A plus b whole raised to power x whole raised to power n. Integration of that, that's ax plus b whole raised to power n plus 1 divided by n plus 1, right? However, we could generalize that rule like this. We can actually do this for other functions as well, but only this one is what you would need to use sometimes, or would help you in some cases, in case of power rule. And it looks like this. If you have an expression and you have a power on top of that, and the derivative of this expression that is inside is multiplying outside. The derivative of the expression inside is multiplying outside. Then the integration of this whole thing is just going to be that expression power n plus 1 divided by n plus 1. We'll just add 1 to the power, divide by the new power. We could think of this in terms of the box notation, in case that f of x notation is confusing. So in place of this box, you could have anything, okay? Any expression in terms of x. If we have a power on top of that, and the derivative of this thing is multiplying outside, then the integration of this whole expression can be directly written as that expression power n plus 1 divided by n plus 1. Let me give you an example of that. For instance, sine x into cos x. We could think of it as sine of x power 1 and then cos x outside. So we could say we have sine x. The derivative of that is multiplying outside. So using that rule, we could just say it's going to be sine square x divided by 2. Add 1 to the power, divide by the new power. And that gives you the result directly. Okay. Take another example. In this case, you could try something like this as well. If you had, for instance, sine cube x into cos x with respect to x, you could say that is sine of x whole cube into cos x. If you want to integrate this, the derivative of this thing is multiplying outside. The integration is going to be sine raised to power 4x divided by 4, and that's your integration. Now, in such cases, they often will give you a substitution. They will often give you a substitution in this case. But if they don't give you that substitution, this is often a very efficient way of doing this, that we think of it like this. If the derivative of the inner part is multiplying outside, you add 1 to the power and divide by that new power. Let me give you another example. Let's say you have 5x cubed plus 7 whole raised to power 4 into 15x squared. Now you see, the derivative of the part that is inside, that is multiplying outside, you could integrate it directly like this. You could say add 1 to the power, divide by the new power, and that gives you the result. Take another example. If you have sine of 2x whole squared into cos of 2x, You could think of it like this. You've got something inside the power. What's the derivative of this? Derivative of this is 2 cos 2x. Now we have just cos 2x outside. Can we make it 2 cos 2x somehow? We could say, let's multiply by 2. But to balance that, we'll have to divide by 2 outside. And now this follows that form. So integration of this is just going to be sine 2x power 2 plus 1 divided by 2 plus 1. And that's the integration, right? You can do everything without this as well. It's possible. There will be other methods to be able to do them. But if you know this, in some cases, it becomes very efficient. If you had cos cube theta, we will see later how to do it using substitution. But you could do it using this extended power rule as well. Cos cube theta, we could break that into 2 parts as cos square theta into cos theta, right? And then we could say it's 1 minus sine square theta into cos theta. And then you break it into 2 parts, cos theta minus sine theta whole squared into cos theta. Now, cos theta can be integrated directly to sine theta. And what about this? We can apply the extended power rule on this. And that is, you've got sine theta. The derivative of that is multiplying outside. Just add 1 to the power, divide by the new power. You get sine cube theta over 3. And that's the integration. We could do the same for tan cube as well. We could break that into 2 parts. We often do this using substitution, but this is an alternative. Tan square x into tan x. Then replace tan square with secant square x minus 1 using this identity. And then you break it into 2 parts. You've got secant square into tan x. Now, think of it like this. Is derivative of secant tan? No. The other way around is true. The derivative of tan is secant square. So we could write tan x inside the brackets and say it has power 1. And it has the derivative multiplying outside. That's secant square. We just add 1 to the power, divide by the new power. That's the integration of this. Integration of tan, that we know how to do using the ln rule. We write that as sine over cos and then integrate it using ln. And that's how we could integrate tan cube x. Make sense? So that's called extended power rule. Then finally, we've got integration by substitution. Not finally, but this is another method that we've got. We have some more to go. Integration by substitution. Now, whenever we have substitution, except for a couple of cases that we'll talk about, they will always tell you what substitution to use. They will always tell you what substitution to use. Okay. For example, let's look at the same integral again. If we had to integrate this, they might give you a substitution u equals sine x. Now, this will be given. They will tell you use this substitution in this case, if they ask you to do it by substitution. U equals sine x, let's say they've given you this substitution. Now, how do you use that here? If you replace sine x with u here, you get u into cos x into dx. Now, you also need to get rid of the other x from here. How would you do that? Whatever substitution you're given, you always will first of all differentiate that. So u equals sine x, you find the derivative of that. That gives you du over dx, which is cos x. And then you would make dx the subject so that you can replace this dx with du as well. Because when you convert things to something that's in terms of u, then you want to integrate them in terms of u as well with respect to u. This is with respect to x. We want to integrate with respect to u. So we want to change this to du as well. How would that happen? Whatever substitution you're given, you would always, first of all, differentiate that. Find the derivative of that, make dx the subject, and then in that integral, you input u equals sine x equal to u, and in place of dx, you put du over cos x. Now, in this case, what's happening is cos x and cos x, they get cancelled, and that just simplifies to this. What's the integration of u? That's u square over 2. Now, you could replace that back and write it as sine square x over 2 plus c. That's the result. If you had limits given, we'll talk about what to do in that case. But if you just try to find the integration, you would find this integration like this and then put that substitution back, and that gives you the result. Whenever you have a substitution, the first thing you do is you find the derivative of that so that you can replace this with the other variable as well. So in this example, for instance, this is the substitution, u equals x square minus 2. What you do is you find the derivative of this, du over dx, that's 2x. Make dx the subject, that becomes du over 2x. Put that here. It becomes du over 2x. and put that substitution here as well. That's x square minus 2, replace that with u. So you have e raised to power u and this thing written here. And now you still have an x left there. This x gets cancelled with this x that you had from there. And we have everything converted to u. And now we can integrate this 4e raised to power u. What's the integration of that? This is 4e raised to power u. We'll put that substitution back and we get the result for that. In these examples, you saw that x was getting cancelled itself. Sometimes that's not what happens. For example, in this case, you were given the substitution u equals 2x plus 1. Let's say you were given the substitution. And when you apply that substitution here, first of all, what you have to do is you have to find the derivative of this. Du over dx, what's that? That's 2. Then make dx the subject. That gives you du over 2. And now you put that substitution there. Replace 2x plus 1 with u and replace dx with this. When you do those two substitutions, you get u inside the square root and you have du over 2. But the problem is this x is still there and it's not getting cancelled. How do we get rid of this x now? We had u equals 2x plus 1. We could make x the subject from here. And that gives us that x is equal to u minus 1 over 2. So now we can replace that x here. We can replace that here. Replace x with u minus 1 over 2. And now we've got everything in terms of u, and now we should be able to integrate it. We can only integrate once we have everything converted to the other variable. So now we've got everything converted to u. We've got this product. We don't have to use integration by parts here because it can actually be simplified. You can just multiply this inside and it simplifies to u power 3 over 2 minus u power 1 over 2. Apply power rule on both of them individually, integrate them, put that substitution back, and you get that result. Now, in this case, we also had the limits. In this case, we also had the limits. The lower limit was 2 and the upper limit was 5. Now, the limits are values of x in this case. The original integral is in terms of x. So we had to integrate this in terms of x. Now, when we convert it to u, the limits would also change because these values are values of x. We can't input those same limits there. So you would also change the limits. How would you do that? You would clearly write down what the lower limit is and what the upper limit is. This is very important that you clearly write down the lower and the upper limit separately. What's the lower limit? Lower limit is x equals 2. Upper limit is x equals 5. Use that substitution now. U equals 2x plus 1 to find the corresponding u values. And u turns out to be 5 for the lower limit, 11 for the upper limit. Input those values in that integral now. 5 to 11, these are the limits that we've got. After converting to u, integrate that, input those limits, and you would get the result. And that's the final result that we wanted there. Okay, so that's how substitution works. Whatever substitution is given, you find the derivative of that, put those two things in that expression. If there's any x that is left still, you replace that as well by rearranging this and inputting that in that integral, and you also change the limits. When you change the limits, it's very important that you clearly write down what the lower limit is and what the upper limit is. I will talk about that in a moment, because sometimes what happens is when you change the limits, the lower limit might end up being a bigger value and the upper limit might end up being a smaller value. So that is something that can happen sometimes. If you don't write it clearly, you would mistakenly write the upper limit as the bigger value and the lower limit as the smaller value. But sometimes it might be reversed. We'll have a look at an example for that. So let's say you've got something like this. T equals integration of 10 over 5 minus square root of h. You want to integrate this, limits are from 0 to 4. Now, we have to use the substitution u equals 5 minus square root of h to find the value for t. Now, how do we do that? This is the integral that we're given. We apply that substitution. We find the derivative of that, replace dh with this thing, and replace this denominator with u. Once we do that, we've got this expression. We still have an h there. To get rid of that, we make h power 1 over to the subject here. That gives us 5 minus u. And we also replace this h power 1 over 2 with 5 minus u now. And we end up getting an integral like this. What about the limits now? what are the limits? The lower limit is 0 and the upper limit is 4, right? These are the limits. These are the values of h. What are the corresponding values of u going to be? U turns out to be 5 here and u turns out to be 3 here. And you see the lower limit is 5 and the upper limit is 3. Lower limit is a bigger value. Upper limit is a smaller value. Now when you write that there, you have to be careful. The upper limit is 3. Do not write 5 there for now. And the lower limit is 5. That's not 3. That's what it is. If you just want to find the value of t, then you could just do it like this, and that's perfectly okay. Input, integrate it. After integrating, you input 3 in that. Subtract from that the case when you input 5, and you would get the correct result from that, and that's perfectly okay. That will work for you. Okay. Sometimes in the question, they will ask you to show something. So they might give you this integral and want you to first of all show that t can be written in this form. They might ask you to show that using this substitution, t can be written like this. Now, when they will ask you to show something, they will write the bigger number on top and the smaller number at the bottom, because that's the conventional way of writing limits, that we write the bigger number up above and the lower limit, the smaller number below. Now, how is that possible? How do you change the limits? We were getting 3 here and 5 as the lower limit. They ask us to show this. If that happens, you can change the limits by multiplying the function by -1. So we had -20 here. If we remove minus from there, if we multiply the whole expression by minus, we could switch the limits, and that would give us this expression that they wanted. So in general, you can remember, if you have any limits for an integral, let's say they're a and b, if you want to switch those limits, you want to make them ba, you multiply the function by minus, and then you can switch the limits, right? And if you have, for instance, integration of p minus q with limits a to b, you can switch the limits by writing them as q minus b. Okay, multiply by minus and switch the limits, and that gives you the result. Okay, so you can switch the limits like this. It's not always necessary to do that. Only when they ask you to show something like this, you can do that by multiplying by minus and then converting to that form. The next thing is you need to be able to integrate powers of sine, cos, and tan. Powers of sine, cos, and tan. First of all, we've got odd powers. In odd power, it's only cube that you need to be able to integrate: sine cube, cos cube, and tan cube. How do you integrate sine cube? Integration of sine cube can be done using substitution. So we looked at one method for this, and that was using extended power rule. More often, they will ask you to do this by a substitution. You should remember these substitutions. These are the substitutions that you should memorize, because this is explicitly part of the syllabus, that you need to be able to integrate powers of sine, cos, and tan. So sine cube, cos cube, and tan cube, you should remember their integration. Sine cube is integrated using the substitution u equals cos x. Cos cube is integrated using substitution u equals sine x. And tan cube is integrated using substitution u equals tan x. You need to remember these substitutions. For sine, we use substitution cos. For cos, we use substitution sine. And for tan, we use tan. Okay. Now, how exactly does it work? If we have integration of sine cube, and we want to use this substitution u equals cos x, first of all, we find the derivative of that. The derivative turns out to be this minus du over sine x. Now, when you do this, you would actually, since you want to put u equal to cos x here, there's no cos there. How do you get cos? You could break sine cube into two parts. You could say that's sine squared x into sine x. You could break it into two parts. And when you do that, you can write sine squared as 1 minus cos squared. And now this cos square can be replaced with u squared. And then you replace dx with this expression as well. Simplify that, and you get a simple integral from that, which is just 1 minus minus into 1 minus u squared, which becomes u squared minus 1. What's the integration of u squared minus 1? U cube over 3 minus u. And then you can put that substitution back. If there are limits, you can change the limits and input those limits here as well. But that's how it would work. For sine cube, use the substitution u equals cos x. Similarly, for cos cube, use integration sine. In this case, we have cos cube of 2x. So the substitution would be u equals sine 2x. Okay. Then you use the standard process, you find the derivative of that. This is again a cube. You want to use the substitution for sine. How do you convert cos to sine? You break it into two parts, cos square into cos square into cos square into cos power 1. You break it into two parts like that. And then you apply that substitution. It becomes 1 minus u squared with du outside and 1 over 2 dividing outside like this. That's coming from here, this 2. Integrate it, input those substitutions back, and you get the result from that. Okay, so for cos cube we use substitution sine. Similarly for tan we use this. For tan cube we use the substitution u equals tan x. Now how would that work? We have to find the derivative of that. Derivative of tan is secant square, and then we make dx the subject, which gives us du over secant square x. Put these two things there, u cube, and then dx can be replaced with du over secant square x. All right. Now, how do you integrate this further? There's still an x there. How do we get rid of this x? We can use the identity for this. 1 plus tan square is secant square. So it can be written as 1 plus tan square. U is tan x, so it becomes 1 plus u squared. Now it's an improper fraction. Integrate it like an improper fraction, quotient plus remainder over divisor, and then put that substitution back, and you get the result from that. Again, this is one way of doing this. The other way is using that extended power rule. This is how you could do this integration of odd powers. For sine cube, cos cube, and tan cube, you either have to memorize these substitutions because sometimes they would not tell you these substitutions. Okay, you either have to memorize these substitutions. For sine cube, you use cos. For cos cube, we use sine. For tan cube, we use tan. You either use these or you remember that extended power rule that we discussed. One of these two methods, you either have to memorize these substitutions or use that extended power rule, right? So they can be integrated both ways. It's your choice now, whichever of them you want to use, but you have to be able to integrate them without any help from the examiner. So they might not tell you the substitution and you still might have to do it. You can do that substitution yourself or use extended power rule. That's your choice. Okay, make sense? All right, then we have even powers of sine, cos, and tan. Even powers include square and power 4, power 2 and power 4. Now for sine and cos, the even powers are integrated using the double angle identity for cos. So sine square, how is that integrated? Using the double angle identity for cos 2a is identical to 1 minus 2 sine square a. We will be using that identity for this. Make sine square the subject, and that gives you sine square a identical to 1 minus cos 2a over 2. So that means sine square x therefore can be written as 1 minus cos 2x over 2, and then it can be integrated directly. We could write that 2 outside from the denominator, and we just have this left, 1 minus cos 2x, that we know how to integrate. Integration of 1 is just x, integration of cos 2x is sine 2x over 2, and that gives us the result from that. Okay, so for sine square, we use this double angle identity. These are even powers are integrated using identities like this. We cannot use the power rule on either this or the previous examples for odd powers, because for power rule, remember we had the condition. For the previous case, we could use the extended power rule as we discussed. But in this case, we can't even use that because we can't write it in that form such that we have the derivative of 1 multiplying outside. We have to use identities for this. We can't use the simple power rule on this like this, that sine cube x is sine cube x divided by 3 and divided by the derivative of sine x, which is cos x. That would be wrong, because remember that rule only used to work for linear expressions. Sine of x whole squared, this expression inside is not linear. Linear is just mx plus c, right? The straight line, that's linear. Sine is a curve like this. That's not linear. You cannot use the simple power rule in this. That would not work. So you have to somehow get rid of this power. So this double angle identity helps us get rid of that power. so that we just have cos of 2x, and then we can integrate that directly like this. So even powers are integrated using they're integrated using the trigonometric identities. Yes, if we had cos of 4x, integration of cos 4x would be sine 4x divided by 4. That's correct. Okay, now let's move on. What about cos square x? For cos square x as well, we use the double angle identity for cos. But the other form now, cos 2a is identical to 2 cos square a minus 1. This is another form for that identity. Make cos square a the subject here, and that gives you this 1 plus cos 2a divided by 2. Put that here, and then you can integrate this separately, and that gives you the result. If you had sine square of 2x, what about this now? Sine square of 2x, how would you integrate this? Again, using the double angle identity for cos 2a is 1 minus 2 sine square a. We can make sine square a the subject here. When we do that, when we make sine square the subject, that leaves us with 1 minus cos 2a divided by 2, right? Now, we don't just have x here, we have 2x. Now we have to think about this identity. When we have sine square a here, on the right side, it's becoming 2a. So whatever is the angle on the left side in this identity, in this form, on the right side, it's double that. When we have 2x here, on the right side, we'll have 2 times that becomes 4x. So sine square 2x can be written as 1 minus cos 4x divided by 2. And then we just integrate it like before. Integrate 1 separately, cos 4x separately, and then simplify that further. Similarly, you could have cos square of half x, for instance. What about this now? Again, we could do it the same way. The double angle identity for cos. For square, even powers, we'll be using the double angle identity for cos. That's the standard. Cos 2a, that is 2 cos square a minus 1. Again, we can make cos square a the subject. Cos square a equals this. And now we think about this. Whatever is the angle here, that's a. On the right side, it becomes 2 times that. If we have half x here, on the right side, 2 times half x, what would that become? That will become x. So this could be replaced with 1 plus cos x over 2. We could write 2 outside and integrate this 1 plus cos x. That can be done directly, and that gives us the integration, right? So that's how we integrate even powers of sine and cos. What about tan square? That's straightforward. Tan square can be written as secant square x minus 1 using this identity. Using this identity, you could write that as secant square x minus 1. And then integration of secant square is tan, integration of 1 is x. And that gives you the result, right? So tan square is pretty straightforward. What about power 4? Now, when you have power 4, generally they will make you do it in multiple parts. In the first part, they will ask you to prove some kind of an identity. And then in the next part, they would want you to integrate this. So you would be able to use the identity from the first part to integrate this in the next part then. But if you had to do it directly, how would you think about it? You'll have to apply the double angle identity twice. So think about this. Sine raised to power 4x. This is what you have initially. Now, how do we get rid of this power, right? That's the idea. We want to get rid of the power so that we can integrate it like before. Now, this is power 4. We could write sine raised to power 4 as sine square x and sine square x whole squared. And then sine square x, it could be replaced with this, just like before, the double angle identity for cos. Sine square a turns out to be this from that. So sine square x, therefore, can be replaced with this 1 minus cos 2x divided by 2 whole squared. And now we've got a minus b whole squared inside the bracket in the numerator. We can expand that, a square minus 2ab plus b squared. Now, we could write 4 outside. This 4, that will simplify things for us. In the numerator, we've got 1. 1 can be integrated directly. That's not a problem. Cos 2x, this can also be integrated directly. The only problem is cos square of 2x. This is still a square. How do we get rid of the square now? Again, we use the double angle identity for cos. Cos 2a is identical to 2 cos square a minus 1. In this case, we've got cos square. So we use the cos square form. That's 2 cos square a minus 1. Make cos square the subject. Cos square a equals this. And now we have cos square of 2x there. Replace a with 2x. If you have 2x here, the angle on the right side should be 2 times that. So if it's 2x, that should be 4x. We have seen that before. So this becomes 1 plus cos 4x divided by 2. And now the powers are all eliminated. We can integrate them now. 1 integrates to x, cos 2x integrates to sine 2x over 2, cos 4x integrates to sine 4x over 4, 1 integrates to x. And then we just simplify all of that and we get the result. If you had to integrate cos raised to power 4, the process for that will be exactly the same with just a difference of some plus minus, but the overall process will be pretty much the same as this. Okay. This is all that we have in integration as far as the concepts are concerned. These are all the concepts of integration. If you remember these rules well, all of these rules, then you would find that the integration questions are not going to be as complicated. The reason why a lot of students find integration difficult is because they don't remember these rules. If you don't even know the rules, then you can't, solve problems. Even if they're relatively easier. And you would find once you know all of these different methods, you would not get something that's very different 95% of the times. Yes, there will be some rare questions in which you'll have to think a bit more, but generally you will be able to figure them out fairly easily if you've done enough practice. So overall, just a quick review of that. If you have any simple function without any product or fraction, use direct formulas that we discussed in the very beginning. If you have a product, you can either use substitution, that will always be given, unless you have sine cube, tan cube, cos cube. For them, you can memorize those 3 substitutions. Apart from that, if it's any other substitution, that will always be given in the question. The other possibility is integration by parts. If they're not given a substitution, you might be able to do integration by parts, or that extended power rule that we discussed. When you have the derivative of what is inside multiplying outside like this, you could use this extended power rule for products. These are the options that we've got for products. For fractions, we've got a number of rules. You might be given a substitution. In that case, you just use that substitution. You have the ln rule then, tan inverse rule, partial fractions. After partial fractions, you could integrate using ln or tan inverse then. Then you have these 2 specific forms of partial fractions that are given in the formula sheet directly. You could split the numerator. You could use the improper fraction method, break it down into quotient plus remainder over divisor if it's an improper fraction. And then if none of them work, you could take the denominator to the numerator. For example, if you have 4 over 2x plus 5 whole raised to 2x plus 1 whole raised to 5, in this case, you can just take the numerator to take the denominator to the numerator. It becomes a power function. You can apply the power rule in this. In this case, you could take x to the numerator and then apply integration by parts on this. So if none of those fraction rules work, you can take the denominator to the numerator like this. Even powers of trig functions, they are integrated using the trigonometric identities. Odd powers, they are integrated using substitution or the extended power rule. This is something that's very common in some recent papers. 4 over cos square. How do you integrate this? 4 over cos square. So 4 is not important, but the fact that you have cos square in the denominator. Now this is in the denominator. You don't use trigonometric identities for this, as in for cos square, you don't use the double angle identity. You only do that when that's in the numerator, right? This is in the denominator. Now this is cos square. Now a lot of times you end up forgetting about this, or it doesn't click at that time at that point. But since it's coming quite often, just remember when you have cos square in the denominator, think of whether you can take it to the numerator like this. When you bring it to the numerator, it becomes secant square. And integration of secant square, we know directly integration of secant square is actually tan. So it can be integrated directly to tan. Okay, so when you have cos square in the denominator, you bring that to the numerator, that becomes secant square. And then that it integrates to tan like this. Okay. Now, these are some examples from some recent papers. I'll quickly show you those examples. In this case, for instance, in the first part, they made you prove an identity. So you'll do that using trigonometric identities. And then they ask you to find this integral. You would have to use that identity, make cos cube theta the subject in that identity. So you proved this, cos 3 theta is identical to this. Make cos cube theta the subject. That gives you this. And replace that expression with that. So a lot of times what happens is they make you prove something in the first part, and then you have to use that in the next part. So when you replace it with this integration becomes quite straightforward. After that, integrate it, input limits, and you get the result. Now, when you're doing integration and you have limits given, a lot of times they want exact answers from you at the end. It's very important that you show all steps in that. When you input limits, you have to make sure that you show that step in which you're inputting the limits. And if they want exact values, you'll have to show more steps as well. And if you're getting something in terms of logs, then you have to write your final answer as a single log, single log term, right? If you have multiple log terms in the final answer, it's necessary to write them as a single log term at the end. Okay. Let's look at this example. In this case, in the first part, they asked you to prove this identity, and then they wanted you to integrate this. Cot x, how do you integrate cot x? Cos over sine. And then you input limits. Make sure that you use exact values because they want exact values from you, and you get the result from that like this. In the third part here, you have cosecant of 2x. In the third part, you have cosecant of 2x. How do you integrate this now? Do we know how to integrate cosecant? We do not have a direct rule for this. So how do we do that? Now, in this case, they have not used the word hence. Otherwise, in a lot of such cases, they would use the word hence, and that will give you a hint that you have to use the previous part. But sometimes they just won't use that and leave it for you to think about it, to figure it out yourself. Cosecant 2x, we don't have a method that we have done to be able to integrate this directly. However, in the first part of this question, you have proved this identity that cosecant 2x can be written as cot x minus cot of 2x. Even though the question does not hint you towards that, you've done that in the first part of this question. You should be able to use that. Use cosecant 2x identical to cot x minus cot 2x, put that in this integral, and then integrate those two separately. So you say cosecant 2x can be written as cot x minus cot 2x. And then you know how to integrate cot x. Cot x, in fact, you've already done in the previous part. That gave you half ln 2. You can just put that there. Cot 2x, you write that as cos 2x over sine 2x. You could write that as cos 2x over sine 2x. And that can then be integrated using the ln rule. What's the derivative of the denominator? Derivative of denominator is 2 cos 2x. So we multiply by 2 here, and to balance that, we divide by 2 outside. And then we just simplify that. We apply the ln rule and input limits, simplify everything, and we get the final result from that. Right. So these calculations tend to be quite lengthy sometimes. You have to be careful in your working about plus minus signs, using exact values, and you have to save yourself from careless errors. Now, these are just some examples now. What I'll do is I will show them to you quickly, and then you can have a look at them in your own time. I'll be skipping through some of them, and then just focus on a few that I think have something that's important in terms of concepts. So I'll quickly scroll through them. I'll slowly scroll through them so you can have a look at them as well. And if there's something that I want to mention in particular, I will do that. So this is integration of sine squared 2 theta. That's the second part. Yeah. So you have this function. They want you to find the area under the graph. You use the formula for area under graph, area between graph and x-axis, integration of y with respect to x, using the substitution x equals sine theta. Now, how do you use the substitution? You find the derivative of this first of all, and then write it like this: dx equals cos theta into d theta. Replace in this dx equal to cos theta d theta and x with sine theta, and then just simplify that. You'll need some simplification until you get something like this. Sine square theta into cos square theta. Now, this is very important. When you have a product like this, sine theta and cos theta multiplying. Now, how would you integrate this? You might think of integration by parts here, but this should remind you of something. When you have sine theta and cos theta multiplying, you have an identity that has these two things multiplying. And that's the double angle identity for sine. Sine 2a is identical to 2 sine a cos a. You could use that here because when that is rearranged, we get half sine 2a equal to sine a cos a, square both sides. And sine square a cos square a, that can be written as 1/4 sine square 2a. We could replace it with that. So it just leaves us with half sine square 2 theta. And that is what we wanted to prove in the second part, that integration can be written like this, sine square 2 theta. So that was a double angle. We got this sine square theta into cos square theta. So we had to use that double angle identity to convert it to that. And then how do we integrate this? We've talked about this before. Sine square 2 theta, we'll have to use double angle identity for cos for this, integrated input limits, and you would get the result from this. Okay, I'll answer your questions later on. This is another question that you can have a look at. A bit complicated, but a one-off. So I'll just, scroll through it. Does this have anything important? Okay, so sometimes you can end up getting infinity as one of the limits. This used to happen in paper 1 as well. There as well, it used to happen sometimes. You would have infinity as one of the limits. Now, all you have to do is just integrate like you would normally do. In this case, they've asked you to use a substitution for this. Now, when you use the substitution, how do you change the limits now? The substitution is u equals x power 1/2. If x is going from from 3 to infinity, then what about u? U would be under root 3. Under root infinity, what's that? That is still infinity. If you take square root of infinity, that is still infinity. So these are the limits that you have there from under root 3 to infinity. Now, how would you deal with them? You integrate it like you normally do. It ends up being tan inverse of u after integration. Right? 1/u square plus 1 integration of that is just tan inverse of u. Now you input the limits, it becomes tan inverse of infinity minus tan inverse of square root of 3. Now, tan inverse of square root of 3, you can evaluate this on your calculator. What about tan inverse of infinity? For this, you'd have to think about the function tan yourself. When is tan equal to infinity? When is tan of something going towards infinity? Think about the graph of the tan function. What does the graph of tan function look like? It starts from 0 at pi/2. It goes towards infinity like this. So you would not be able to do that on your calculator. You would have to do it yourself. Think of the graph of tan function. It goes towards infinity when it's going towards pi/2. So tan inverse of infinity, when you have here, you would write that as pi/2. And then you simplify that, you get your result. That's pi/3. Right? So tan inverse of infinity, that is pi/2. Sometimes in these problems, you end up getting infinity in the denominator. So if you have anything over infinity, for example, 4/infinity, that is basically 0, because 4 divided by an extremely large number, that is 0. But in this case, we have tan inverse of infinity. That is when tan approaches pi/2. And that was something different that I saw in one of those questions. Let me scroll through further. Okay, sometimes they make you do something like this. In the first part, they wanted you to differentiate this cos x over sin x to show that the derivative of cot x is minus cosecant square x. And that's the first part of this question. So you write cot x as cos x over sin x, then differentiate it using the quotient rule, and that gives you minus cosecant square x. And then in the second part, they want you to integrate this thing, x into cosecant square x. Now, whenever you have something done in the first part like this, it will always have some use in the next part afterwards. Now, how can you use this first part in the next part? X into cosecant square x. It's a product. We apply integration by parts on this. U equals x, v dash equals cosecant square x. Now, how do we integrate cosecant square x? In the previous part, we proved that the derivative of cot is minus cosecant square. So what will be the integration of cosecant square? That will be minus cot x. Now, this is from 2019. In the recent papers now, you from 2020 onward, you actually have this given in the formula sheet as well, as I showed you earlier. This integration is already given to you. So now you could use that directly. But if it was something else, and that they made you do something in the first part, find the derivative of something, in the next part, you should know that whatever you found as the derivative here, that means the integration of this thing is going to be cot x. So you could use that in the next part, right? Now for cosecant square x, we saw in the very beginning of this session that cosecant square integration of that is minus cot x. That's written in the formula sheet as well. So that's what you use there. Then you just apply integration by parts, simplify that further, input limits. It becomes a fairly difficult calculation because of those square roots involved, and then a lot of calculation. You want an exact answer as well, I assume. Okay, sorry. Yeah, you want an exact answer as well. That means you need to show working. So you do it step by step like this. Convert the multiple log terms to a single log term if there are any, and then you get that final result that they wanted there. Okay. Similarly, you find other questions. For example, this is the function. In the first part, it's about differentiation. We'll skip that. In the second part, they want you to use this substitution and partial fractions to find the exact value of this integral. Now, f of x was this fraction. How do you integrate this? They've given you a substitution, and that is u equals e raised to power x. You use that substitution. After using that substitution, you end up getting this. Now, how do you integrate this? They gave you a hint in the question that you have to use partial fractions. Even if they did not give you that hint, you should have been able to think about it yourself, that you can factorize the denominator into two parts like this, and then use partial fractions, and then integrate that separately. Now, in this case, they've given you a hint, but it's not necessary that they would always give you that hint. You would think of this fraction. Can you use the ln rule? Tan inverse, partial fractions. When you think about partial fractions, think about whether you can factorize the denominator or not. In this case, you can, so you should do that. Okay. Next, you just do it using partial fractions and then simplify everything. That's a pretty long working. They want an answer in this form, ln a. That means a single log term. Where a is rational, that means it could be a fraction, but it should be a single log term, not multiple log terms. So when you get the answer, it turns out to be something like this. You have to convert it to a single log term. What you do is the numbers that are multiplying outside, you take them to the powers and then apply the multiplication and division laws to write them as a single log term. You can have a look at this working as well. Sometimes they will give you constants like this, like we saw in differentiation earlier as well. Now, don't worry about them. That's just a constant. Treat it like a constant and just work in terms of that. So in this case, you have x e raised to power minus ax. It's a product. You apply integration by parts in this. U is x, v dash is e raised to power minus ax, and then just apply integration by parts. Don't get worried about a. Just keep writing it as a or minus a. That's just like any other number. For example, it could be -3, -4. So you'll just do everything in terms of a. Eventually, in this case, what happens is when you simplify everything, you get this as the result, and the result is also in terms of a. Now, you have to keep it in exact form like this. Careless errors tend to happen in problems like these when you have constants involved, especially. So you have to be just careful about them. The rest is just standard working. That would work like that. Again, in the first part, they ask you to prove an identity. And then in the next part, they want you to integrate something. Now, they want you to integrate this now, exact value of this integral. Now, in the first part, we proved that this thing was equal to cos 2 theta. So that's one thing that we can do. We can replace this with cos 2 theta. And that can be integrated directly. But the problem is, how do we integrate this? We saw this earlier as well, but in that question, we had a hint given in the question. Here, we are not given any hint. It's just 4 sine square theta cos square theta, and we're left to figure it out on our own how to integrate this. Sine into cos, that should remind you of something. Sine and cos multiplying, if they have the same power, you can use the double angle identity for sine. Sine 2 theta is 2 sine theta cos theta. If you square that, that becomes sine square 2 theta, that equals 4 sine square theta cos square theta. So you can replace this right inside with sine square 2 theta. And then we know how to integrate that. We've discussed that before as well. Use the double angle identity for cos to get rid of that power, integrate that, input those limits that are given, and you want an exact answer at the end again. So you have to show all working, and you get the result from that. Okay. This is another example. In the first part, they wanted you to convert it to this form. First of all, r cos of something plus alpha. You did that. And then in the next part, they want you to integrate this. So that's the same expression in the denominator, 3 cos 2x minus under root 3 sine of 2x. You've got that in the denominator here, and there's a square on top of that. Now, in the first part, you've already converted that denominator to this form. So you replace it with that form. And then in the denominator, now you have cos of something. When you square that whole thing, it becomes cos square of that. Right? And you have constant here, 3 over 12. You could write that outside to simplify things, 1 over 4 outside like this. And then inside the integral, we have 1 over cos square. Does that remind you of something? 1 over cos square. When we have cos square in the denominator like this, when you have cos square in the denominator like this, we could bring that to the numerator so that it becomes secant square. And we know how to integrate that directly. Integration of secant square is tan. We integrate that, and then we just input those limits and get our result from that. Okay. When you have a constant a like that, like we saw in the previous example, it's not necessary that they would tell you in the question that you have to give an answer in terms of a. Sometimes you have to figure it out yourself, as in from the question statement and from the context. You need to understand yourself that the answer will be in terms of a. It would not get eliminated, and that's all right. You would just leave it in terms of a. They would not always tell you that it has to be in terms of a. It's kind of going to be understood from the context of the question. This is another example. You can have a look at this working. There's nothing new here as such, but we just have to, apply that substitution, use that identity here as well. 1 plus tan square is secant square. Then we have secant square in the denominator. When you bring that to the numerator, you have cos square, and use that double angle identity to integrate that further. Again, you have something in terms of a. In the first part, they wanted you to find partial fractions, and the fractions that you have are in terms of a here. Now, in this question, they are telling you that the answer has to be in this form: p ln q plus r ln s, where p and r are integers and q and s are prime numbers. Even though this is in terms of a, they want the final answer not to have. They want the final answer not to have a in it, right? You would just do it the standard way. A is just a constant, remember, so its derivative would be 0. So the derivative of x plus 2a, that is 1. That's the ln form. This is also ln form. This is also ln form. You integrate all of them, input those limits from minus a to plus a, and then convert that to a single log. And do they want a single log? No, they don't want a single log in this case. You just simplify everything. The a's get cancelled. Now, this is actually important because in this case, what we're getting is this is ln of 3a, and this is ln of 7a, and this is ln of a. They don't want any a in the final answer. So the question is telling you the final answer should not have an a, right? How do you get rid of a from here now? You break it down like this. Ln of 3a can be written as ln of 3 plus ln a. Ln of 7a can be written as ln of 7 plus ln a. And then you simplify everything. L and A's will get cancelled as it's happening here. And you just are left with this. And that's your final answer. So you need to be very good at using the laws of logarithms here as well. Volume questions, they do come, but in paper 3, they're very rare. Mostly you get area questions, but volume questions do come sometimes as well, as in they are part of the syllabus. But in recent questions, you won't find many of them. It's mostly area that's tested in paper 3. But volume is indeed part of the syllabus. That is part of the syllabus. This is another example. You had to find this area, integration of sine x into cos 2x. Now, how would you do that? Integration of sine x into cos of 2x. Now, one idea is that you break it down and you expand this double angle as 2 cos square x minus 1. Simplify that and you get 2 cos square x into sine x here and sine x here. And then on the first integral, you could use the extended power rule as we discussed. That's one idea. Use the extended power rule here. So it becomes derivative of cos x is minus sine x. So we put minus outside, and to balance side, we put a minus outside, and it becomes that form. We use the extended power rule in this, and integration of sine is just minus cos, and then we integrate it like this. That's one idea. This is a fairly complicated example if you do it yourself the first time. Because if you think of integration by parts does not work. The loop method also does not work here because you don't end up getting that loop in this. And it does not become any simpler. So you either have to use the extended power rule, that's one idea, or the alternative here could be that you break it like this again. You say sine x into 1 minus 2 sine square x, and that could be broken down into two parts like this: sine x into 2 sine of cube x. Integration of sine x sine cube x, then you could either use extended power rule for this as well, as we discussed earlier, or you could use the substitution as we covered. So for sine cube x, use the substitution u equals cos x, and then you apply that process for that substitution and input the limits at the end, and you would get the result using this as well. Okay, so I hope that was helpful. That's many different types of questions that I've showed you here. Have a look at them. Why does the loop not work here? You do end up getting a loop in this question, but I think I remember trying this once. But what happens in this case is you end up getting an I on the left side and an I on the right side as well. So it ends up getting cancelled out. So instead of having a minus I on the right, it ends up being a plus I. So it's the same coefficient on both sides, and it ends up getting eliminated. So you don't get anything useful from that. So that kind of doesn't work in this case. But you can use one of these two methods, right? Okay, so I hope that was helpful and I did not scare you too much with this. Now let me know if there are any questions.